There's a monster in the night sky. You can't see it with your naked eye from most places on Earth, but it's there. A colossal spiral of 1 trillion stars, slowly spinning in the darkness. And it's hungry. For billions of years, this galaxy has been hunting, devouring, consuming other galaxies whole, ripping them apart star by star, and absorbing their remains into its ever-growing body. The evidence is written in streams of stars that stretch for hundreds of thousands of light years, scars from ancient cosmic crimes, stellar graveyards orbiting a galactic predator. This is Andromeda, our nearest major galactic neighbor, and right now, as you sit here watching this video, it's speeding toward us at over 100 kilometers per second. For decades, scientists believed the outcome was inevitable. The Milky Way, our home galaxy, would collide with Andromeda in about 4 billion years. It was one of the few things about the distant future we thought we knew for certain. But in 2025, everything changed. A groundbreaking study published in Nature Astronomy revealed something shocking. The collision might not happen at all. The odds? About 50-50. A cosmic coin flip. And the chances of it happening in that classic 4 billion year time frame astronomers talked about for so long? Only about 2%. The reason? The universe is far more complex than we realized. Gravitational interference from the Large Magellanic Cloud, uncertainties in our measurements, the influence of smaller galaxies like Triangulum. All of these factors create a future that's far less certain than we thought. So what does this mean? It means the universe is even more mysterious than we imagined. It means the story of galactic collisions is more nuanced, more intricate, more fascinating than we ever knew. Tonight we're going to explore it all. The evidence that Andromeda has been eating galaxies for billions of years. The science of why galaxies collide and why they sometimes don't. And the remarkable discovery that our cosmic future hangs in the balance, uncertain, waiting to be written. Welcome to the story of Andromeda, the galaxy that ate its neighbors and might or might not eat ours next. Hello, and welcome to Science for Sleep. I'm so glad you're here. If you're new to the channel, this is your place for deep, long-form space documentaries designed to satisfy your curiosity while you relax, unwind, or drift off into a peaceful sleep, where we explore the biggest mysteries in the universe with the depth they deserve. No rushed 10-minute summaries here. Just you, me, and the cosmos. And if you're a regular viewer, thank you for coming back. Your support makes these deep dives possible. If you haven't already, please consider subscribing and hitting that bell icon so you never miss a journey into the unknown. And if you enjoy this video, a like really helps us reach more curious minds like yours. Tonight's topic is one I've been excited to explore, especially now with the latest 2025 discoveries. Andromeda, the Andromeda Galaxy, also known as Messier 31 or M31. It's the closest major galaxy to our own Milky Way, sitting about 2.5 million light years away. On a dark night, far from city lights, you can actually see it with your naked eye, a faint smudge of light in the constellation Andromeda. It's the most distant object visible to the unaided human eye. Think about that for a moment. When you look at Andromeda, the light hitting your retina left that galaxy 2.5 million years ago, before modern humans even walked the Earth. But Andromeda isn't just beautiful. It's a cosmic predator. For billions of years it has been consuming other galaxies, ripping them apart through tidal forces and absorbing their stars, gas and dark matter. We have the evidence. We can see the stellar streams, long rivers of stars that trace the orbits of galaxies that Andromeda destroyed millions or even billions of years ago. We can identify the victims that are being eaten right now, galaxies in their final death throes, spiraling into Andromeda's gravitational embrace. And the Milky Way? For decades, astronomers believed we were definitely next, that Andromeda was heading straight for us and collision was inevitable. In about 4 billion years, give or take, the two galaxies would collide. They'd merge, they'd become one. But here's where the story gets really interesting. In June 2025, a team of astronomers led by Till Sawala published a study in Nature Astronomy that completely changed our understanding. Using advanced simulations that included factors earlier models had overlooked, particularly the gravitational influence of the Large Magellanic Cloud and realistic uncertainties in Andromeda's motion, they discovered something remarkable. The collision is far from certain. In fact, it's about a 50-50 chance, a cosmic coin flip. About half of their simulations showed a merger happening within the next 10 billion years. The other half, the galaxies miss each other or interact so weakly that no significant merger occurs. And that classic collision timeline of 4 billion years that's been in textbooks for over a decade, the probability of that specific scenario dropped to just 2%. This changes everything. It means the universe is more unpredictable, more complex, and frankly more fascinating than we thought. The future of our galaxy isn't written in stone. It's a probability cloud, a range of possibilities, a cosmic uncertainty. Over the next 2.5 hours, we're going to explore this story in full. Here's what we'll cover together. First, we'll look at the crime scene. The evidence that Andromeda has been eating other galaxies. We'll talk about stellar streams, tidal disruption, and how astronomers pieced together the history of Andromeda's violent past. You'll meet the victims, the small galaxies currently being torn apart, and learn how scientists discovered more than 30 past meals hidden in Andromeda's halo. Then we'll zoom out and ask the big question: why do galaxies eat each other? What are the forces at play? How does gravity work on these immense scales? We'll explore the dark matter, halos that dominate galactic mass and make these interactions possible. Next, we'll dive into the 2025 revelation. What did Sawala's team discover? What's the Large Magellanic Cloud got to do with it? Why did earlier predictions get it wrong? And what does it mean to live in a universe where even galactic collisions are uncertain? We'll explore multiple possible futures. What happens if the galaxies do collide? What happens if they don't? What might a close encounter look like? One that disrupts both galaxies and without leading to a full merger. We'll walk through each scenario, examining the implications for stars, for planets, and potentially life. We'll also look at what this teaches us about galaxy evolution. If the Milky Way Andromeda merger is uncertain, what about other galaxy pairs across the universe? How many predicted collisions might not actually happen? How does this change our understanding of how galaxies grow and evolve? And then, in the final chapters, we'll go even deeper. We'll ask what this uncertainty means philosophically. What does it tell us about prediction, about knowledge, about our place in a universe that's far more complex than our models suggest? By the end, I promise you'll see Andromeda and the universe itself in a completely different light. Not just as a beautiful neighbor, but as a reminder that the cosmos is full of surprises, that even our most confident predictions can be wrong, and that uncertainty, rather than being frustrating, makes the universe all the more wondrous. So grab something comfortable, settle in. Let's explore the galaxy that ate its neighbors, and let's confront the fascinating reality that we don't actually know if the Milky Way is next. Let's begin with what we do know for certain. Andromeda is a galactic cannibal. This isn't speculation or prediction. This is documented fact, written in the stars themselves. How do we know Andromeda has been eating other galaxies? You can't exactly watch a galaxy devour another one in real time. These processes take hundreds of millions or even billions of years. So how did astronomers figure it out? The answer lies in something called stellar streams. Imagine you have a small galaxy, a dwarf galaxy, with maybe a few billion stars orbiting a much larger galaxy like Andromeda. As this dwarf galaxy orbits, Andromeda's immense gravity begins to pull on it. But here's the key: gravity doesn't pull evenly. The side of the dwarf galaxy that's closer to Andromeda feels a stronger pull than the side that's farther away. This difference in gravitational force is called a tidal force. Over time, these tidal forces stretch the dwarf galaxy. Stars on the near side get pulled toward Andromeda faster, and stars on the far side lag behind. The dwarf galaxy gets elongated, pulled into a cigar shape, Eventually, stars start getting stripped away from the dwarf galaxy entirely. They form long streams of stars that trace the dwarf's orbit around Andromeda. Think of it like a river of stars, or a trail of breadcrumbs marking where the victim has been. These stellar streams can be enormous. We're talking structures that stretch for hundreds of thousands of light years. And because stars move relatively slowly compared to the vast distances involved, these streams can persist for billions of years. They're like fossils, cosmic fossils that tell the story of galactic destruction. Now, detecting these streams is incredibly difficult. Stars in a stream are very spread out and they're faint. Andromeda is 2.5 million light years away. So we're talking about detecting individual stars or small clumps of stars across a mind-boggling distance. But modern telescopes have made it possible. Surveys like the Pan-Andromeda Archaeological Survey, or PANDAS, have used the Canada-France-Hawaii telescope to map out millions of stars in and around Andromeda. And what they found was astonishing. Andromeda's halo, the diffuse cloud of stars surrounding the main galaxy, is full of structure. It's not a smooth, uniform glow. It's lumpy, streaky, filled with loops and arcs and shells of stars. These structures are the remnants of destroyed galaxies. Every stream, every arc, every shell is the graveyard of a dwarf galaxy that Andromeda tore apart. One of the most prominent features is called the Giant Southern Stream. This is a massive arc of stars stretching over 150,000 light years, looping around the southern part of Andromeda's halo. It's one of the largest and most obvious stellar streams we've ever detected. The stars in this stream are moving together. They share similar velocities, and their chemical compositions are distinct from the stars in Andromeda's main disk. All of this points to a common origin. They were once part of a single dwarf galaxy that Andromeda devoured. How long ago did this happen? Based on the positions and velocities of the stars, astronomers estimate that the dwarf galaxy that created the giant southern stream was disrupted roughly 2 to 3 billion years ago. The stars in the stream have been orbiting Andromeda ever since, slowly spreading out, gradually mixing into the halo. In another few billion years, the stream will be so dispersed that it will be nearly impossible to detect. The evidence of the crime will have faded. But right now, we can see it clearly. And the giant southern stream is just one example. PANDAS and other surveys have identified dozens of streams and substructures in Andromeda's halo. Each one represents a destroyed galaxy. By counting these structures and modeling their orbits, astronomers have estimated that Andromeda has consumed at least 30 dwarf galaxies over its lifetime. Some of those galaxies were devoured billions of years ago. Others are being torn apart right now as we speak. But stellar streams aren't the only evidence. There's another way to detect galactic cannibalism. Look for the victims that haven't been fully digested yet. Galaxies that are currently in the process of being destroyed. These are the smoking guns. Andromeda has two prominent satellite galaxies that are visible in most telescope images. They're called Messier 32 or M32 and Messier 110 or M110. Both are dwarf elliptical galaxies, much smaller than Andromeda, and both orbit relatively close to Andromeda's core. For a long time, astronomers thought these were just normal satellite galaxies, peacefully orbiting their massive neighbor, but then they looked closer. M32 is a compact elliptical galaxy, very dense with a lot of stars packed into a small volume. It sits about 8,000 light years across, which is tiny compared to Andromeda's 220,000 light year diameter. But here's the weird part. M32 is way too dense for a dwarf elliptical. It has more mass concentrated in its core than it should given its size, and its outer regions are distorted. The edges of M32 are stretched and warped as if something has been pulling on it. That something is Andromeda. M32 is being tidally disrupted. Andromeda's gravity is pulling stars away from M32's outer edges, stripping the galaxy of its material. Over time, M32 will lose more and more of its mass, until eventually it will be completely absorbed into Andromeda. Some astronomers think M32 may have once been a much larger spiral galaxy, perhaps similar in size to the Milky Way's satellite, the Large Magellanic Cloud, but after repeated close passes by Andromeda's core, it lost most of its outer stars and gas, leaving only the dense central core that we see today. In other words, M32 is a galaxy that has already been mostly eaten. It's a stripped core, a remnant, a ghost of what it once was. And it's still being consumed. M110 is in a similar situation. It's a bit larger than M32, roughly 17,000 light-years across, and it orbits farther from Andromeda's core. But M110 also shows signs of tidal distortion. Its outer regions are elongated and asymmetric, stretched by Andromeda's gravity. Observations have detected streams of stars extending from M110 toward Andromeda, clear evidence that stars are being pulled away. M110 is being eaten alive, losing mass with every orbit. Both M32 and M110 are victims in progress. They're being destroyed slowly over hundreds of millions of years. Eventually, they'll vanish entirely, their stars mixed into Andromeda's halo, adding to the faint glow of background light that surrounds the galaxy. And it's not just these two. Andromeda has at least 20 known satellite galaxies, small dwarf galaxies orbiting in its gravitational field. Many of these satellites are also showing signs of tidal disruption. They're losing mass, they're being stretched, they're all on death row, waiting for the final encounter that will rip them apart. But here's where the story gets even more interesting. Andromeda didn't just eat a bunch of random dwarf galaxies. Some of the galaxies it consumed were themselves the products of earlier mergers. Andromeda has a history of eating galaxies that had eaten other galaxies. It's a hierarchy of cannibalism. How do we know this? By studying the chemistry of stars in the halo. Stars that formed in different galaxies have slightly different chemical compositions. They have different ratios of heavy elements like iron, magnesium, and calcium, depending on the history of supernovae and star formation in their parent galaxy. By measuring the chemistry of halo stars, astronomers can group them into populations that came from different progenitor galaxies. And what they found is that some of these populations overlap. Some streams contain stars with mixed chemistries, suggesting that the dwarf galaxy that was destroyed had itself consumed another galaxy in the past. It's cannibalism all the way down. This paints a picture of Andromeda's history as one of relentless growth through violence. Over billions of years, Andromeda has grown larger and more massive by consuming everything in its vicinity. It's a process called hierarchical galaxy formation, and it's thought to be the dominant way that galaxies grow in the universe. Small galaxies merge to form medium galaxies. Medium galaxies merge to form large galaxies. And large galaxies like Andromeda grow even larger by continuing to consume their smaller neighbors. But there's a twist. Andromeda hasn't just been eating little guys. There's evidence that Andromeda has experienced major mergers in the past, collisions with galaxies comparable in size to the Milky Way. How do we know? By looking at the structure of Andromeda's disk. Andromeda's disk isn't smooth. When astronomers map the motions of stars in the disk, they find that stars at different distances from the center are moving in strange ways. Some are moving faster than expected. Some are moving slower. Some are even moving in the opposite direction from the rest of the disk. This is exactly what you'd expect if Andromeda's disk was disrupted by a major merger in the past. The collision would have scrambled the orbits of stars, creating these kinematic anomalies. In fact, simulations suggest that Andromeda experienced a major merger roughly 2 to 3 billion years ago, around the same time that the giant southern stream was created. Some scientists think these two events might even be related. The major merger could have disturbed the orbits of smaller satellite galaxies, sending them plunging into Andromeda and creating the streams we see today. And before that, there's evidence for an even older major merger, roughly 8 to 10 billion years ago. This collision likely played a major role in forming Andromeda's thick disk and bulge. Essentially, much of Andromeda's current structure is the result of violent collisions. Let's pause and take in what this means. Andromeda, this beautiful spiral galaxy that we admire in the night sky, is a cosmic crime scene. Its halo is filled with the ghosts of destroyed galaxies. Its satellites are being slowly devoured. Its disk bears the scars of ancient collisions. And all of this is just what we can detect. There are likely many more small galaxies that Andromeda consumed billions of years ago. Galaxies whose streams have long since dispersed and become undetectable. This is certain. This is documented. Andromeda is a cannibal. It has eaten more than 30 galaxies and it's still eating. But what about the Milky Way? Is our galaxy next on the menu? For decades, scientists said yes, absolutely. But that answer, as we'll discover, is more complicated than anyone realized. First though, we need to understand why galaxies collide in the first place. What forces are at play on these immense scales? That's what we'll explore in the next chapter. Because once you understand the rules of the game, you'll understand why the outcome is so much more uncertain than we thought. So why does this happen? Why do galaxies consume each other? To answer that, we need to talk about gravity, dark matter, and the structure of the universe on the larger scales. Let's start with a simple fact. Galaxies are not static. They move, they orbit, they interact. When we look at images of galaxies, it's easy to think of them as frozen in place, isolated islands of stars floating in an empty void. But that's an illusion. The universe is a dynamic, evolving place. Galaxies are constantly moving through space, driven by the gravitational pull of other galaxies and the overall expansion of the universe. In regions where galaxies are relatively close together, like in galaxy groups or clusters, gravitational interactions are common. Galaxies tug on each other. They alter each other's orbits, and sometimes they collide. Now, when we say galaxies collide, we need to be clear about what that means. Galaxies are mostly empty space. Stars are separated by vast distances. The average distance between stars in the Milky Way is about 4 to 5 light years. That's roughly 30 trillion kilometers. So when two galaxies pass through each other, the chances of individual stars actually colliding are incredibly tiny, almost zero. But even though stars don't collide, the galaxies themselves do. Because galaxies are held together by gravity, and gravity has infinite range. When two galaxies come close, their gravitational fields interact. Stars, gas, dust, and dark matter all feel the pull of the other galaxy. Orbits get disrupted, structures get distorted, and if the encounter is close enough, and if the conditions are right, the two galaxies can become gravitationally bound to each other. They'll orbit each other, pass through each other multiple times, lose energy through a process called dynamical friction, and eventually merge into a single, larger galaxy. This process can take billions of years. It's not a quick, violent crash. It's a slow, gravitational dance that gradually transforms both galaxies. Now, there are different types of galactic interactions, depending on the masses of the galaxies involved and the geometry of their encounter. When a small galaxy encounters a much larger galaxy, we call that a minor merger. The small galaxy is typically torn apart by tidal forces, and its stars are absorbed into the larger galaxy's halo. This is what's happening to Andromeda's satellite galaxies like M32 and M110. It's also what happened to the dwarf galaxies that created the stellar streams in Andromeda's halo. Minor mergers are common, and they're the primary way that large galaxies like Andromeda and the Milky Way grow over time. But when two galaxies of similar mass collide, we call that a major merger. Major mergers are much more dramatic. The two galaxies disrupt each other significantly. Stars get flung into chaotic orbits. Gas clouds collide and compress, triggering intense bursts of star formation called starbursts. The central supermassive black holes of both galaxies eventually sink to the center of the merged system and merge themselves, releasing tremendous amounts of energy in the form of gravitational waves and, in some cases, powerful jets of radiation. Major mergers completely transform the galaxies involved. If two spiral galaxies collide, the result is often an elliptical galaxy. The ordered rotation of the spirals gets scrambled into the random, chaotic orbits that characterize elliptical galaxies. This is actually thought to be one of the main ways that elliptical galaxies form. So why has there been so much discussion about the Milky Way and Andromeda colliding? It's because we live in a galaxy group called the local group. The local group contains about 80 known galaxies, but the two dominant members are the Milky Way and Andromeda. These two galaxies contain the vast majority of the mass in the local group, and because they are relatively close together, and because they are gravitationally interacting, the question becomes, will they eventually merge? For a long time the answer seemed obvious. Yes, absolutely. Andromeda is moving toward us. Gravity is pulling us together. Eventually we'll collide, but here's where things get more complicated. Now here's where it gets even more interesting. When we talk about the mass of a galaxy, we're not just talking about stars. Stars make up only a small fraction of a galaxy's total mass. The majority of the mass in galaxies comes from something we can't see: dark matter. Dark matter is one of the great mysteries of modern astrophysics. We know it exists because we can see its gravitational effects. Galaxies rotate faster than they should based on the visible mass of stars and gas. The only way to explain this is if there's a huge amount of invisible mass surrounding the galaxy, providing extra gravitational pull. We call this invisible mass dark matter because it doesn't emit, absorb, or reflect light. It interacts with normal matter only through gravity. And dark matter isn't just a small correction, it's dominant. In a galaxy like the Milky Way or Andromeda, dark matter makes up about 85 to 90% of the total mass. The stars, gas, planets, everything we can see, that's only 10 to 15% of the mass. The rest is dark matter. Dark matter forms what we call a halo around each galaxy. This halo is much larger than the visible galaxy. Andromeda's visible disk is about 220,000 light years across, but its dark matter halo extends for roughly 1 million light years or more. That means the dark matter halos of the Milky Way and Andromeda are actually already overlapping. In a sense, the two galaxies are already interacting gravitationally, even though the visible disks are still far apart. And this dark matter halo is crucial for understanding galactic interactions. When two galaxies approach each other, the first things to interact are the dark matter halos. Dark matter particles pass through each other without colliding directly. They don't interact via electromagnetism, but the overall gravitational field changes. The dark matter halos merge first, and then the visible galaxies follow. This is important because dark matter dominates the dynamics of any potential collision. The trajectories of the galaxies, the timing of any merger, the final structure of any merged system, all of this is controlled primarily by dark matter. When astronomers run simulations of galactic interactions, they have to include dark matter. If you only simulate the stars, you get the wrong answer. Now let's talk about tidal forces in more detail, because they're central to the process of galactic cannibalism. Tidal forces arise because gravity weakens with distance. If you have an extended object, like a galaxy, the part of that object that's closer to a massive body experiences a stronger gravitational pull than the part that's farther away. This difference in force stretches the object. Imagine you're standing on a small moon orbiting close to a massive planet. Your feet, which are closer to the planet, feel a stronger pull than your head. If the planet is massive enough and you're close enough, the difference in gravitational pull between your feet and your head can be enormous. This is the same principle that causes tides on Earth. The moon's gravity pulls more strongly on the side of Earth facing the moon than on the far side, creating bulges of water that we experience as high tides. For galaxies, tidal forces are immensely powerful. When a dwarf galaxy orbits close to a massive galaxy like Andromeda, the tidal forces stretch the dwarf galaxy. Stars on the near side are pulled ahead and stars on the far side lag behind. Over multiple orbits, stars get stripped away, forming the stellar streams we talked about earlier. But tidal forces don't just strip stars, they also strip gas. And gas is where things get really interesting. Gas clouds in the dwarf galaxy get stretched and compressed. When gas is compressed, it can collapse and form new stars. So tidal interactions can actually trigger star formation in the victim galaxy. This leads to a burst of blue, young stars forming along the tidal tails, creating beautiful, luminous arcs of star formation. We see this in many interacting galaxy systems. It's like a last gasp of life before the galaxy dies. At the same time, gas from the dwarf galaxy can be funneled toward the center of the larger galaxy. This gas can feed the central supermassive black hole, causing it to grow. It can also trigger star formation in the larger galaxy's disk, so galactic interactions aren't just destructive. They can also drive the evolution of galaxies, shaping their properties and influencing their star formation histories. Another key concept is dynamical friction. This is a process by which a moving object loses energy as it plows through a background of other objects. Imagine you're trying to run through a crowded room. Every time you bump into someone, you slow down a little. Dynamical friction is similar, except instead of bumping into people, a galaxy moving through the halo of another galaxy gravitationally interacts with stars and dark matter particles. Each interaction transfers a tiny bit of energy and momentum, gradually slowing the galaxy down. This is crucial for mergers. When a small galaxy is captured by a larger galaxy, dynamical friction causes it to spiral inward over time. Without dynamical friction, the small galaxy might just pass through and escape. But with dynamical friction, each orbit brings the small galaxy closer to the core, until eventually it merges with the central galaxy. Dynamical friction also affects interactions between galaxies of similar mass. Both galaxies plow through each other's halos, losing energy, and their orbits decay. They spiral toward each other, pass through each other multiple times, each time losing more energy, until they finally settle into a single merged system. Now let's zoom out and look at the big picture. Galaxy interactions are happening all over the universe, at all times. In fact, hierarchical structure formation, the idea that large structures grow by consuming smaller structures, is one of the fundamental principles of cosmology. In the early universe, roughly 13.8 billion years ago, matter was distributed almost uniformly, but there were tiny fluctuations in density, tiny ripples in the fabric of space-time left over from the Big Bang. Over time, gravity amplified these fluctuations. Regions that were slightly denser attracted more matter, becoming even denser. This process, called gravitational collapse, led to the formation of the first stars and galaxies. The first galaxies were small, much smaller than the galaxies we see today. But as time went on, these small galaxies merged to form larger galaxies. And those larger galaxies merged to form even larger galaxies. This hierarchical process continues today. The universe is a cosmic food chain, where galaxies grow by eating each other. And it's not random. The distribution of galaxies in the universe follows a pattern called the cosmic web. Galaxies are not scattered randomly through space. They're concentrated along vast filaments and sheets with enormous voids in between. These filaments are like the scaffolding of the universe, and galaxies flow along them, driven by gravity. When galaxies move along these filaments and encounter each other, interactions happen. Large galaxy clusters, which contain hundreds or even thousands of galaxies, are the densest nodes in the cosmic web. In these clusters, galaxy interactions are extremely common. Galaxies ram through the hot intracluster gas, getting stripped of their own gas in a process called ram pressure stripping. They experience tidal interactions with other galaxies. Over billions of years, many of the galaxies in clusters merge together, forming giant elliptical galaxies at the cluster center. The local group, which contains the Milky Way and Andromeda, is much smaller than a rich galaxy cluster, but the same principles apply. Andromeda and the Milky Way are the two largest galaxies in the group, and they're gravitationally dominant. The question is, what exactly will happen when two massive galaxies in a small group interact? For decades. The answer seems straightforward. Measure Andromeda's velocity, run the simulations, predict the outcome. But as we're about to discover, the universe had a surprise in store, because predicting the future of galactic interactions is far more difficult than anyone realized. And that's what we'll explore in the next chapter. The measurements, the models, and the shocking 2025 discovery that changed everything we thought we knew about the fate of the Milky Way and Andromeda. Let's talk about how we know Andromeda is moving toward us in the first place. Because measuring the motion of something 2.5 million light years away is incredibly difficult. There are two components to Andromeda's motion that we need to measure. First, there's the radial velocity, the speed at which Andromeda is moving directly toward or away from us along our line of sight. Second, there's the tangential velocity, the component of motion perpendicular to our line of sight, the sideways motion across the sky. The radial velocity is relatively easy to measure. We use the Doppler shift. When an object is moving toward you, the light waves it emits get compressed, shifted toward the blue end of the spectrum. When an object is moving away from you, the light waves get stretched, shifted toward the red end of the spectrum. By measuring how much the spectral lines from stars in Andromeda are shifted, we can calculate how fast Andromeda is moving toward or away from us. And the answer is, Andromeda is moving toward us at about 110 kilometers per second. That's the radial velocity. It's been known for decades and is very well measured, but the tangential velocity is much harder to measure. To detect sideways motion, you need to measure how Andromeda's position in the sky changes over time. But Andromeda is so far away that its motion across the sky is incredibly tiny. Even moving at hundreds of kilometers per second, it takes years or even decades to detect any change in position. For a long time, astronomers simply didn't have the precision to measure Andromeda's tangential velocity. They knew it was moving toward us, but they didn't know if it was moving straight toward us or at an angle. And that matters enormously. If Andromeda has a large sideways velocity, it might miss us entirely, swinging past the Milky Way without colliding. But if the sideways velocity is small, a collision becomes much more likely. This uncertainty persisted until 2012, when a team led by astronomer Roland van der Marel used the Hubble Space Telescope to finally measure Andromeda's tangential velocity. They did this by tracking the positions of individual stars in Andromeda over several years and measuring how those positions changed. It's an incredibly difficult measurement, requiring Hubble's extraordinary precision. But they succeeded. What they found was that Andromeda's tangential velocity is very small, essentially consistent with zero within the measurement uncertainties. That means Andromeda is moving almost directly toward us. There's very little sideways motion. This was a big deal. It meant that a head-on collision or something close to it was likely. Based on these measurements, van der Marel's team ran simulations. Their results, published in multiple papers between 2012 and 2014, predicted that the first close encounter between the Milky Way and Andromeda would happen in about 3.9 billion years, with a final merger occurring around 6.4 billion years from now. These predictions became widely cited. They appeared in textbooks, documentaries, and popular science articles. For over a decade, the collision of the Milky Way and Andromeda was presented as one of the few certainties about the distant future of our cosmic neighborhood. But there was a problem. The simulations made certain assumptions. They modeled the Milky Way and Andromeda as isolated objects interacting only with each other. They didn't fully account for other gravitational influences in the local group. And most importantly, they didn't fully account for the measurement uncertainties in Andromeda's tangential velocity. Remember, van der Marel's team measured the tangential velocity as consistent with zero, but there were error bars. The true velocity could be slightly higher or slightly lower than zero, and those error bars, though they might seem small, translate into huge uncertainties over billions of years and millions of light years. Additionally, the original simulations treated the large Magellanic Cloud, a substantial satellite galaxy orbiting the Milky Way, as a minor player. The LMC contains roughly 15 billion stars and perhaps 10 to 20% of the Milky Way's mass when you include its dark matter halo. That's not insignificant. And the LMC is not sitting still. It's orbiting the Milky Way, and its gravitational pull affects both the Milky Way and to a lesser extent, Andromeda. For years, astronomers assumed these effects were small enough to ignore. The LMC is much smaller than the Milky Way or Andromeda, so surely its influence wouldn't change the big picture, right? Wrong. In June 2025, a team led by astrophysicist Till Sawala at the University of Helsinki published a study in Nature Astronomy that turned the conventional wisdom upside down. They ran a new set of simulations, state-of-the-art models that included the Large Magellanic Cloud's gravitational influence and realistic uncertainties in Andromeda's tangential velocity. They ran thousands of simulations, each with slightly different initial conditions, to explore the full range of possible outcomes. And what they found was shocking. In only about 50% of the simulations did the Milky Way and Andromeda merge within the next 10 billion years. In the other half, the galaxies either missed each other entirely or had such weak interactions that no significant merger occurred. The classic prediction of a collision around 4 billion years from now. That scenario appeared in only about 2% of the simulations. This was a bombshell. The collision that astronomers had been confidently predicting for over a decade was suddenly far from certain. It wasn't inevitable. It was a coin flip. So what changed? What did Sawala's team account for that earlier models missed? That's what we'll explore in the next chapter. Because understanding why the prediction changed tells us something profound about the nature of scientific knowledge, the limits of prediction, and the beautiful complexity of the universe. Let's dive into what Till Sawala's team discovered and why it changes everything. The key insight is that the future of the Milky Way and Andromeda doesn't depend only on these two galaxies. It depends on the entire local group. Every galaxy, every dark matter halo, every gravitational interaction matters. And when you account for all of these factors, and when you honestly represent the uncertainties in our measurements, the picture becomes much more complex. Let's start with the Large Magellanic Cloud, or LMC. The LMC is a satellite galaxy of the Milky Way, visible from the southern hemisphere as a fuzzy patch of light. It's about 160,000 light-years away from us, which means it's relatively close on cosmic scales. It contains roughly 15 billion stars, making it one of the largest satellite galaxies in the local group. For a long time, the LMC was treated as a minor character in the story of the local group. It's much smaller than the Milky Way or Andromeda, so its gravitational influence was assumed to be negligible when considering the Milky Way-Andromeda interaction. But here's what we've learned. The LMC is more massive than we thought. When you include its dark matter halo, the LMC might contain 10 to 20% of the Milky Way's total mass. That's substantial. And the LMC is not sitting still. It's on a highly elliptical orbit around the Milky Way, plunging through the Milky Way's dark matter halo at high speed. As the LMC orbits, it exerts a gravitational pull on the Milky Way. This pull affects the Milky Way's overall motion. It changes the Milky Way's trajectory through space, and that in turn affects how the Milky Way and Andromeda approach each other. Think of it like this. Imagine you're trying to predict whether two balls on a pool table will collide. If the table is perfectly flat and there are no other balls, the prediction is straightforward. You measure the velocities, you calculate the trajectories, and you predict the collision. But now imagine there's a third ball on the table. A smaller ball that's moving and exerting its own gravitational influence. If pool balls had gravity. Suddenly, the prediction becomes more complicated. The third ball might nudge one of the larger balls slightly, changing its trajectory just enough that it misses the other ball entirely. Or it might push it into a collision that wouldn't have happened otherwise. That's what the LMC does. It's the third ball on the table. And its influence, though smaller than the Milky Way's or Andromeda's, is enough to change the outcome over billions of years and millions of light years. Sawala's team included the LMC in their simulations, along with its dark matter halo and its orbital motion. And they found that the LMC's gravity can alter the trajectory of the Milky Way just enough to turn a collision into a near miss, or vice versa. But the LMC isn't the only factor. There's also the Triangulum Galaxy, also known as M33, Triangulum is the third largest galaxy in the local group, smaller than the Milky Way and Andromeda, but still substantial. It contains about 40 billion stars and sits roughly 2.7 million light years from the Milky Way. Triangulum is also approaching Andromeda. In fact, some simulations suggest that Triangulum might collide with Andromeda before the Milky Way does, or that Triangulum could interact with both the Milky Way and Andromeda during the merger process. The gravitational influence of Triangulum adds another layer of complexity to the system. And then there are the measurement uncertainties. Van der Marel's 2012 measurement of Andromeda's tangential velocity was a remarkable achievement, but it came with error bars. The measurement showed that the tangential velocity is small, but it could be slightly positive or slightly negative, and the exact value matters. Here's why. Even a small difference in tangential velocity, say 10 or 20 kilometers per second, might seem negligible compared to Andromeda's overall velocity of 110 kilometers per second toward us. But over billions of years, that small difference adds up. It can be the difference between a direct collision and a near miss. Sawala's team accounted for these measurement uncertainties by running simulations with a range of initial conditions, each one within the error bars of the observations. Some simulations had Andromeda moving slightly faster sideways. Some had it moving slightly slower. Some had the LMC on a slightly different orbit, and so on. When you run thousands of simulations like this, you get a distribution of outcomes, and that distribution is eye-opening. About 50% of the simulations resulted in a merger between the Milky Way and Andromeda within the next 10 billion years. About 50% resulted in no merger at all. In some of the no merger cases, the galaxies passed close to each other, close enough to disrupt each other's structures, but then swung apart and never merged. In other cases, the galaxies missed each other entirely, passing by at a safe distance with minimal interaction. And here's the really striking part. The timing of the merger, in the simulations where it did happen, varied widely. Some mergers happened in 4 billion years, some happened in 6 billion years, some happened as late as 8 or 9 billion years from now. The classic prediction of a merger around 4 to 6 billion years appeared in only a small fraction of the simulations, about 2% for the 4 billion year scenario. So what does this mean? It means the future of the local group is far more uncertain than we thought. It's not a single predictable outcome. It's a probability distribution, a cloud of possible futures. And this uncertainty isn't because we don't understand the physics. We understand gravity very well. We understand dark matter, at least well enough to model its gravitational effects. We understand galactic dynamics. The uncertainty comes from two sources: the complexity of the system and the limitations of our measurements. The local group is a complex system with multiple massive bodies interacting gravitationally. Small changes in initial conditions can lead to large changes in outcomes over billions of years. This is a classic example of what's called sensitive dependence on initial conditions, or more popularly, the butterfly effect. In a complex dynamical system, tiny differences in the starting state can cascade into vastly different end states. And our measurements, as good as they are, have limits. We can measure Andromeda's velocity to within a certain precision, but not perfectly. We can estimate the mass of the LMC, but there's uncertainty. We can model the dark matter halos, but we don't know their exact shapes and density profiles. When you combine these uncertainties with the sensitive dynamics of the system, you get a wide range of possible futures. And that's what Sawala's study revealed. Now this might sound frustrating. After all, wouldn't it be nice to know for certain whether the Milky Way and Andromeda will collide? Doesn't the uncertainty make things more confusing? In a sense, yes. But in another sense, this uncertainty is a gift. It's a reminder that the universe is more complex than our models. It's a reminder that prediction, especially over billions of years, is hard. And it's a reminder that the future is not predetermined. It's genuinely uncertain. And that, I would argue, makes the story more interesting. Because now we're not just talking about an inevitable collision. We're talking about a cosmic coin flip. We're talking about multiple possible futures, each one with its own implications. So let's explore those futures. What happens if the galaxies do collide? What happens if they don't? What might a close encounter look like? One that disrupts both galaxies without leading to a full merger. We'll walk through each scenario in the next chapters, because the beauty of the 2025 revelation is that it doesn't close the story. It opens it up. It transforms a single predicted future into a branching tree of possibilities. And each branch is fascinating in its own right. Let's explore the first scenario. The collision does happen. In about half of Sawala's simulations, the Milky Way and Andromeda do eventually merge. So even though it's no longer certain, it's still a real possibility, maybe even the most likely single outcome. What would that look like? Let's imagine we're living in one of those timelines. We're somewhere between 4 and 8 billion years in the future. The exact timing varies, but let's say it's roughly 5 billion years from now. The sun has aged. It's noticeably brighter and hotter than it is today. If Earth still exists in a habitable state, which is unlikely by this point, life would be facing extreme challenges from the increased solar radiation. But let's set that aside and focus on the galactic event. Andromeda has been growing larger in the sky for millions of years. What once appeared as a faint, fuzzy patch now dominates the night sky. It spans a huge portion of the heavens, a glowing spiral of 1 trillion stars stretched across the darkness. It's one of the most spectacular sights anyone could witness, a reminder that we live in a dynamic, evolving universe. And then, the first encounter begins. Andromeda and the Milky Way are now so close that their gravitational influence on each other is overwhelming. The outer regions of both galaxies start to warp and distort. Long tidal tails of stars begin to form, streaming out from each galaxy like cosmic banners. Gas clouds in the disks collide and compress, triggering intense bursts of star formation. Brilliant blue regions light up across both galaxies as millions of new stars are born. And then, the galaxies pass through each other. The Milky Way's disk plunges into Andromeda's disk, and Andromeda's disk plunges into the Milky Way's. For anyone observing from a planet in either galaxy, the sky would be a chaotic swirl of stars, nebulae, and glowing gas clouds. But here's the remarkable thing we mentioned earlier. Even during this close encounter, the chances of any star from one galaxy actually colliding with a star from the other galaxy are almost zero. Stars are separated by vast distances. The space between stars is so enormous compared to the sizes of stars that collisions are extraordinarily rare. So if stars don't collide, what does happen? Orbits get disrupted. Every star in both galaxies is moving in an orbit around its galactic center. In a spiral galaxy, most stars orbit in roughly circular paths within the disk, all moving in the same direction. This gives the galaxy its ordered, rotating structure. But when two galaxies pass through each other, the gravitational field becomes chaotic. Each star suddenly feels the pull of not just its own galaxy, but the other galaxy as well. Stars get tugged in unpredictable directions. Their orbits get perturbed. Some stars gain energy and move to larger orbits. Some stars lose energy and sink toward the center. Some stars get ejected from the galaxies entirely, flung out into intergalactic space, and many stars end up on highly elliptical, tilted orbits that don't follow the original disk structure. After the first encounter, the galaxies swing apart, but they're now gravitationally bound. They'll fall back toward each other for a second encounter, and then a third. Each passage brings them closer together, and each passage further disrupts their structures. Over the course of maybe 1 billion years, the two galaxies merge completely. The spiral arms disappear. The disks dissolve. What emerges is a single, massive elliptical galaxy, a smooth blob of stars with no clear rotational structure. Astronomers have nicknamed this merged galaxy Milkomeda, a combination of Milky Way and Andromeda. Milkomeda will contain roughly 2 trillion stars, the combined stellar populations of both galaxies. It will be one of the largest galaxies in the local universe. But what happens to the solar system? As we discussed earlier, planetary systems remain stable during galactic mergers. The Sun's gravity dominates the solar system out to a distance of about 1 to 2 light years. Even during the chaos of the merger, the nearest stars will still be light years away. The planets, including Earth, if it still exists, will remain in orbit around the Sun. However, the Sun's orbit around the galactic center will change dramatically. Today, the Sun orbits the center of the Milky Way at a distance of about 26,000 light years, completing one orbit every 230 million years or so. But after the merger, the Sun could end up almost anywhere in Milkomeda. Simulations show a range of outcomes. The Sun might be flung out into the halo, tens or even hundreds of thousands of light years from the center. It might sink toward the core, ending up in the dense central bulge, or it might end up somewhere in the main body of the elliptical galaxy, at a moderate distance from the center. A small fraction of stars, roughly 1 to 2%, will be ejected from Milkomeda entirely. These stars will be flung out into intergalactic space, no longer bound to any galaxy. If the Sun is one of these ejected stars, the night sky would become profoundly dark. No more Milky Way band of light. No nearby galaxies visible with the naked eye. Just a handful of the nearest stars and the distant, faint glow of galaxies millions of light years away. But most likely the Sun will remain part of Milkomeda. And the night sky, for any observers that far in the future, will look completely different. The familiar band of the Milky Way will be gone. Instead, stars will be scattered throughout the sky in all directions, part of the elliptical distribution of Milkomeda. There's also the question of the central supermassive black holes. Both the Milky Way and Andromeda have supermassive black holes at their centers. The Milky Way's black hole, Sagittarius A, has a mass of about 4 million times the mass of the Sun. Andromeda's black hole is much larger, with a mass estimated between 110 and 230 million solar masses. When the galaxies merge, these two black holes will spiral toward each other over millions of years, driven by dynamical friction. Eventually they'll merge, releasing an enormous burst of gravitational waves, ripples in space-time itself. For a brief moment, this black hole merger will emit more power in gravitational waves than all the stars in the observable universe combined emit in light. If any advanced civilizations exist in Milkomeda at that time, and if they have gravitational wave detectors sensitive enough, they'll witness one of the most powerful events in the universe. After the merger, Milkomeda will have a single, even more massive supermassive black hole at its center, with a mass exceeding 100 million solar masses. Now, let's talk about star formation during the merger. When the gas clouds of the two galaxies collide, they compress. This compression triggers a burst of star formation, a starburst. For a few tens of millions of years, Milkomeda will be one of the brightest galaxies in the local universe, with massive young stars lighting up regions across the merging structure. But this starburst phase won't last. After the gas is used up or expelled, star formation will slow to a trickle. Milkomeda will begin its long decline into old age. Over billions of years, the bright blue stars will age and die. The galaxy will gradually turn redder, as only long-lived, low-mass stars remain. Trillions of years from now, Milkomeda will be a faint, red elliptical galaxy, slowly fading as its stars burn out one by one. This is the collision scenario. It's dramatic, transformative, and cosmically significant. And even though it's no longer certain, it's still possible. Maybe even likely, but it's not the only possible future. So let's explore the alternative. What happens if the galaxies don't merge? Now let's consider the second scenario. The galaxies don't merge. They pass close to each other, maybe even close enough to disrupt each other's structures, but they never complete a full merger. This happened in about half of Sawala's simulations. What would that look like? In this scenario, Andromeda still approaches the Milky Way. It still grows larger in the sky over millions of years. The dark matter halos still interact. Gravity still pulls the two galaxies toward each other. But the timing and geometry are slightly different. Maybe Andromeda's tangential velocity is just a bit higher than in the collision scenario. Maybe the Large Magellanic Cloud's gravitational pull nudges the Milky Way onto a slightly different trajectory. The details vary from simulation to simulation, but the key point is that the galaxies don't become tightly bound to each other. They pass by each other, they interact gravitationally, but they don't merge. In some versions of this scenario, the encounter is relatively distant. The galaxies pass within a few 100,000 light years of each other, close enough to feel each other's gravity, but not close enough for a dramatic disruption. Some tidal distortion occurs, some stars might get stripped from the outer regions, but overall, both galaxies survive the encounter relatively intact. After the passage, the galaxies swing apart. They might eventually fall back toward each other for a second encounter, millions or billions of years later, but the second encounter is also weak. Over time, the galaxies settle into new orbits, possibly orbiting each other at a distance, or possibly drifting apart slowly. In other versions of this scenario, the encounter is much closer. The galaxies might pass within 50,000 to 100,000 light years of each other. At that distance, tidal forces are strong. Both galaxies get significantly distorted. Long tidal tails of stars stream out. Gas clouds collide, triggering bursts of star formation. The disks warp and bend, but even with all this disruption, the galaxies don't merge. They're moving too fast relative to each other, or at too much of an angle, to become gravitationally bound. They pass through each other, suffer significant damage, and then fly apart. This is sometimes called a hit-and-run encounter. The galaxies hit each other, or at least graze each other, and then run away before they can settle into a merger. What happens to the galaxies after a hit-and-run encounter? They're wounded. Their structures are disrupted. Stars that once orbited peacefully in the disk are now on chaotic orbits. The spiral arms might be distorted or partially destroyed. Gas clouds have been compressed and heated, triggering star formation in some regions while shutting it down in others. Over time, both galaxies will try to recover. Gravity will pull things back together. The disrupted structures will partially heal, but the galaxies won't look quite the same as they did before. They'll bear the scars of the encounter. For the Milky Way, a close encounter without a merger might actually be less disruptive than a full merger. The Sun's orbit would still be perturbed, but probably not as dramatically. The solar system would remain intact. The night sky would change, especially during the closest approach, but after the galaxies separate, things might eventually settle back into a new equilibrium. In this scenario, the Milky Way remains a distinct galaxy. It doesn't merge with Andromeda. Billions of years from now, astronomers in the Milky Way, if they exist, would look out and see Andromeda in the distance, perhaps still relatively nearby, perhaps orbiting the Milky Way at a distance, perhaps slowly drifting away. There's also a third possibility within the near-miss scenario, a very distant encounter. In some of Sawala's simulations, the galaxies miss each other by a large margin, passing by at distances of 500,000 light years or more. At that distance, the gravitational interaction is weak. There's still some effect. Dark matter halos overlap, orbits get slightly perturbed, but the disruption is minimal. In this version, Andromeda grows large in the sky, then slowly recedes as it passes by. The encounter is visible, but not dramatically disruptive. Both galaxies continue on their separate paths, largely unaffected. This is the most anticlimactic outcome, but it's also a real possibility. The universe doesn't always deliver dramatic collisions. Sometimes galaxies just miss each other. Now, which of these outcomes will actually happen? We don't know. That's the whole point of the 2025 revelation. The future is uncertain. It depends on factors we can't measure precisely enough, and on the complex interplay of multiple gravitational influences. But here's what we can say. Each of these scenarios teaches us something different about galaxy evolution. The collision scenario teaches us how elliptical galaxies form, how supermassive black holes merge, and how major mergers drive star formation and transform galactic structures. The near-miss scenario teaches us that galaxy interactions don't always lead to mergers. Galaxies can suffer significant disruption and still survive as distinct entities. This is important for understanding galaxy populations across the universe. Not every close encounter leads to a merger. And the distant encounter scenario teaches us that predictions are hard. Even when two galaxies appear to be on a collision course, the outcome is uncertain. Small differences in velocity or trajectory can mean the difference between collision and near miss. All of this is valuable. It enriches our understanding of how galaxies evolve, and it reminds us that the universe is full of surprises. But there's another layer to this story. What does this uncertainty mean for life? If the collision is uncertain, does that change how we think about the fate of life in the Milky Way and Andromeda? That's what we'll explore in the next chapter, because the collision, or lack thereof, has profound implications for any civilizations that might exist in either galaxy. Let's think about life. Not just life on Earth, but life anywhere in the universe. If the Milky Way and Andromeda both contain billions of stars, and if even a tiny fraction of those stars have planets in their habitable zones, and if even a tiny fraction of those planets harbor life, then we're talking about potentially billions of living worlds. For decades, when scientists talked about the fate of life during the Milky Way Andromeda collision, the message was reassuring. Don't worry, planetary systems will survive. Stars won't collide. Planets will stay in orbit. Life, for the most part, will be fine. And that's still true, but now there's an interesting twist. The collision might not happen at all. So what does that mean for life? Let's break it down by scenario. In the collision scenario, life can survive, but with risks. We've already discussed the main dangers. Increased supernova rates in starburst regions, close stellar encounters that might disturb Oort clouds and trigger comet impacts, and radiation from the active galactic nucleus if the central black holes become highly active during the merger. But for most planetary systems, including our solar system, if it still exists, these risks are low. The vast majority of stars will be far from starburst regions. Close stellar encounters will be rare, and most stars will remain at safe distances from the galactic center, so life can survive a galactic collision. It's been pointed out by astrobiologists that galaxy mergers are common in the universe, especially in the past when galaxies were closer together and interactions were more frequent. If life were fragile enough to be wiped out by galactic collisions, it would be extremely rare. But we exist, which suggests life is resilient enough to endure these events. However, there's a subtle point. While individual planetary systems might survive, the broader galactic environment changes. Spiral galaxies like the Milky Way and Andromeda have ongoing star formation, creating new planetary systems and new opportunities for life to arise. But after a merger, star formation slows dramatically. Once the gas is used up, no new stars form and no new planets form. So a merger could mark the end of new life in the merged galaxy. Existing life could persist for billions of years, but new life would stop arising. In the near-miss scenario, especially if the encounter is distant or only moderately disruptive, life might actually be better off. The galaxies remain distinct. Star formation continues. New planetary systems keep forming. The galactic environment remains relatively stable, apart from the temporary disruption during the close encounter. In this scenario, life in the Milky Way and Andromeda could continue to flourish independently for billions of years longer than it would in a merger scenario. The two galaxies would each maintain their populations of living worlds, evolving separately, with no merger to transform them into a single, aging elliptical galaxy. And there's another interesting implication. If intelligent civilizations exist in both galaxies, a near-miss encounter might bring them close enough to detect each other or even communicate, without the chaos of a full merger disrupting their civilizations. Imagine you're an advanced civilization in the Milky Way, and you watch as Andromeda approaches over millions of years. As the galaxies draw closer, radio signals or light from civilizations in Andromeda might become detectable. You might even be able to establish communication, sending messages across the shrinking gap between galaxies, and then the galaxies pass by each other and begin to separate. The window of opportunity closes, but for a few million years, two separate galactic civilizations were close enough to interact. That's a fascinating scenario. It suggests that galactic encounters, even ones that don't lead to mergers, might create brief windows of opportunity for intergalactic contact. Of course, this is all speculative. We don't know if intelligent life exists elsewhere in the Milky Way, let alone in Andromeda, but it's fun to think about. Now there's another question worth exploring. What about the galaxies that Andromeda has already consumed? If Andromeda has eaten more than 30 dwarf galaxies, and if those galaxies had stars and planets, what happened to any life that might have existed there? This is a sobering thought. Each of those dwarf galaxies might have contained millions or billions of stars. If even a small fraction had habitable planets, we're talking about potentially millions of worlds, and all of them were disrupted when their galaxies were torn apart by Andromeda. For life on a planet in one of those doomed galaxies, the immediate effects might have been minimal. The planet's star would still shine. The planet would still orbit. But over millions of years, the parent galaxy would disintegrate around it. Star formation would cease as gas was stripped away. The stellar neighborhood would grow sparser as the galaxy spread out into a stream. Eventually, that planet's star would find itself in Andromeda's halo, far from the dense regions where most stars reside. The night sky would grow darker. The galaxy that once surrounded it would be gone, absorbed into Andromeda. If the planet harbored intelligent life, that civilization would witness the slow death of its galaxy. They'd watch as their cosmic neighborhood dissolved. They'd see stars drift apart, the galactic center fade, and the structure of their galaxy vanish over millions of years. Could they have done anything about it? If they were advanced enough, perhaps. They might have been able to migrate to safer star systems, or build habitats in space, or even leave their galaxy entirely before it was completely absorbed, or they might have simply accepted their fate, adapted to the changing environment, and continued their existence in the halo of Andromeda, isolated and far from other civilizations. We'll never know. These galaxies were destroyed billions of years ago. Any life that existed there is long gone, and any evidence of it has been scattered and mixed into Andromeda's halo. But it's a reminder that the universe is not just beautiful and awe-inspiring, it's also indifferent. Galaxies consume each other without regard for the life that might exist within them. Entire worlds are disrupted. Entire ecosystems might be destroyed. And the universe doesn't care. Yet life persists. Life adapts. Life survives. And even in a universe where galaxies collide and die, life finds a way to continue. And now, with the 2025 revelation, we know that the future is uncertain. The collision might happen. It might not. But either way, life will likely endure, because life is resilient. It's one of the most resilient phenomena in the universe, and that's a hopeful thought. No matter what happens, no matter whether the Milky Way and Andromeda merge or miss each other entirely, life will go on. The story will continue. Now, we've talked a lot about the science, the physics, the fate of galaxies and stars and planets, but there's another layer to this story, a philosophical layer. What does it mean to live in a universe where even galactic collisions are uncertain, where our most confident predictions can turn out to be wrong? That's what we'll explore in the next chapter, because the 2025 revelation teaches us something profound about knowledge, prediction, and our place in the cosmos. Let's step back and think about what the 2025 Sawala study really means, not just for astronomy, but for how we understand knowledge and prediction. For over a decade, the collision between the Milky Way and Andromeda was presented as one of the few certainties about the distant future. Astronomers said, "We don't know much about what will happen billions of years from now. But we do know this, the galaxies will collide, it's inevitable." That certainty was comforting in a way. It gave us a solid prediction about the deep future. It was something to point to and say, look, we can predict the cosmos. We understand how gravity works. We can run the simulations. We know what will happen. But now we know that certainty was premature. The collision is not inevitable. It's uncertain. And that uncertainty isn't because we're missing some piece of physics. It's because the system is complex, because our measurements have limits, and because small uncertainties in initial conditions lead to large uncertainties in outcomes over billions of years. This is a humbling revelation. It reminds us that prediction is hard, especially over long time scales. It reminds us that the universe is more complex than our models, and it reminds us that confidence in scientific predictions must always be tempered by an honest assessment of uncertainties. But here's the thing. This uncertainty is not a failure of science. It's a success. Because science is not about being certain. Science is about being honest about what we know and what we don't know. The earlier predictions weren't wrong in the sense of being based on bad science. They were based on the best available models and measurements at the time, but they didn't fully account for all the factors, and they didn't fully represent the measurement uncertainties. The 2025 study improved on those earlier predictions by including more factors and representing uncertainties more honestly. That's how science progresses. We refine our models, we improve our measurements, we discover new complexities, and our predictions become more accurate, even if that accuracy sometimes means acknowledging greater uncertainty. So what does this mean for other astronomical predictions? Should we doubt everything astronomers say about the future? Not exactly. It means we should understand predictions as probability distributions, not certainties. Some predictions are very confident. For example, we're very confident that the Sun will expand into a red giant in about 5 billion years. The physics of stellar evolution is well understood, and the uncertainties are small. But other predictions, especially those involving complex gravitational interactions over billions of years, are less certain. And that's okay. Uncertainty doesn't mean ignorance. It means we understand the limits of our knowledge. And there's something beautiful about that, because it means the future is not predetermined. It's genuinely uncertain. It's open. Multiple futures are possible, and we don't know which one will actually occur. This has profound philosophical implications. It means that the universe is not a deterministic clockwork where everything is pre-scripted. It's a complex, chaotic system where small changes can lead to large differences in outcomes. It also means that prediction, and at its core, is about probabilities, not certainties. And that's a more honest and more interesting way to think about the future. Now let's zoom out even further. What does the Milky Way Andromeda story teach us about our place in the universe? First, it teaches us humility. We live on a small planet, orbiting an ordinary star, in a galaxy that may or may not collide with another galaxy billions of years from now. The universe is vast, and we are a tiny part of it. The fate of our galaxy is uncertain, and it will unfold over timescales far longer than human civilization has existed. But second, it teaches us empowerment. Because even though we're small, we're capable of understanding the universe. We can measure the motion of a galaxy 2.5 million light years away. We can run simulations that explore billions of years of cosmic evolution. We can grapple with the deep questions of existence and come up with meaningful answers, even if those answers include uncertainty. And third, it teaches us to appreciate the present. The Milky Way, as it exists today, is a temporary configuration. Whether it merges with Andromeda or not, it won't look the same billions of years from now. Galaxies change, stars are born and die, structures come and go, but right now, the Milky Way is here. It's a beautiful spiral galaxy, full of stars and gas and planets and quite possibly life. And we're part of it. We're living in this moment, this brief window of time when the Milky Way is at its peak, when star formation is still ongoing, when the night sky shows the galactic band arcing overhead. That's precious. It's temporary, but it's precious. And the uncertainty about the future doesn't diminish that. If anything, it enhances it, because it reminds us that nothing lasts forever, that change is the only constant, and that each moment is unique and irreplaceable. There's also a broader lesson about science and society. In a world that often demands certainty, that wants simple answers to complex questions, science offers something different. Science offers honest uncertainty. It offers the best predictions we can make with the information we have, along with an acknowledgement of what we don't know. And that's valuable, because it's a model for how we should approach other complex problems, whether it's climate change, public health, economic forecasting, or any other area where we're trying to predict the future. We should be honest about uncertainties. We should represent our predictions as probability distributions, not certainties. And we should update our predictions as we learn more. The 2025 Sawala study is a perfect example of this. When new information became available, when better models were developed, the predictions changed, and the scientific community acknowledged that change. That's how it should work. Now let's bring it back to the personal level. What does all this mean for you, for me, for anyone watching this video? It means we're part of a cosmic story that's still being written. We don't know how it ends. We don't know if the Milky Way and Andromeda will merge or miss each other. We don't know what the galaxy will look like billions of years from now. But we know we're here now. We know we can look up at the sky, see Andromeda as a faint smudge of light, and understand what it is. We know that light left Andromeda 2.5 million years ago, before humans existed, and traveled across the void to reach our eyes. We know that Andromeda is a galaxy of 1 trillion stars, that it has a violent history, that it's moving through space, and that its future is uncertain. And knowing that, understanding that, is a profound privilege. It connects us to something much larger than ourselves. It reminds us that we're part of the universe, and the universe is part of us. So when you look up at Andromeda tonight, or the next clear night you have, remember this. You're looking at an uncertain future. You're looking at a galaxy that might one day merge with ours, or might pass by and drift away. You're looking at a cosmic coin flip that won't be resolved for billions of years. And that's beautiful. That's profound. That's the universe as it really is. Complex, uncertain, and endlessly fascinating. Now we're nearing the end of our journey. We've explored the evidence of Andromeda's cannibalistic past. We've looked at the physics of galactic interactions. We've examined the 2025 revelation and what it means for the future. We've considered the fate of life and the philosophical implications of uncertainty. But there's one more thing we need to do. We need to bring it all together. We need to step back and see the big picture. What's the ultimate takeaway from this story? That's what we'll do in the final chapter. The mind blow, the climax, the moment where everything comes into focus. Here we are, the final chapter, the mind blow. Let's start with a simple observation. The universe is not a collection of certainties. It's a landscape of probabilities. For a long time, humans have sought certainty. We want to know what will happen. We want predictions. We want answers, and science has given us many answers. We can predict eclipses. We can calculate the orbit of planets. We can forecast the weather at least a few days out. But the deeper we look into the universe, the more we encounter uncertainty. Not because we're ignorant, but because uncertainty is woven into the fabric of reality. Quantum mechanics tells us that at the smallest scales, particles don't have definite positions or velocities until they're measured. They exist in superpositions of multiple states. The outcome is probabilistic. Chaos theory tells us that in complex dynamical systems, small changes in initial conditions lead to vastly different outcomes. Weather is chaotic. The long-term motion of planets is chaotic. And as we've learned, the interaction of galaxies is chaotic. And now, the 2025 revelation about the Milky Way and Andromeda tells us that even the future of our galaxy, even the large-scale structure of the cosmos, is uncertain. This is the nature of the universe. It's not a clockwork mechanism where everything is predetermined. It's a branching tree of possibilities where multiple futures coexist until one of them is realized. And that's profound because it means the future is not written. It's being written right now through the complex interplay of forces and particles and galaxies across the cosmos. The Milky Way and Andromeda might collide, or they might not. Both futures are real possibilities, existing side by side in the probability cloud until time unfolds and one of them actually happens. And here's the mind blow. This is true for everything, every system, every interaction, every event in the universe is part of this branching tree of possibilities. You are part of it. Your life, your choices, your future, all of it exists in a cloud of probabilities. Some outcomes are more likely than others, but nothing is absolutely certain until it happens. The same is true for humanity as a whole. We might survive for billions of years and spread across the galaxy. Or we might go extinct in the next few centuries. Or we might evolve into something completely different. All of these futures are possible. The probability of each one depends on choices we make, on events we can't predict, on the complex interplay of society and technology and environment. And it's true for the universe itself. The universe might expand forever, cooling into a heat death, or dark energy might change its properties, leading to a different fate, or some new physics might emerge that we haven't discovered yet. We don't know. The future is uncertain. And that uncertainty is not a bug. It's a feature. It's what makes the universe dynamic. It's what makes stories possible. It's what makes the future interesting. Because a predetermined universe would be boring. If everything was certain, if every event was scripted from the beginning of time, there would be no real change, no real choice, no real story. But in a universe of probabilities, every moment matters, every choice matters, every event contributes to which branch of the probability tree actually gets realized. And we're part of that. We're not just passive observers watching a predetermined script unfold. We're participants in the story. Our actions, our choices, our existence, all of it contributes to the unfolding of the universe. Now let's bring this back to Andromeda. The fact that we don't know for certain whether the Milky Way and Andromeda will collide doesn't make the story less interesting. It makes it more interesting. Because now the story is open, it's unfinished, it's genuinely uncertain. And that uncertainty connects us to the cosmos in a deep way. Because we're all living in uncertainty. We're all part of a universe where the future is not written, where multiple possibilities coexist, where the story is still being told. And that's beautiful. That's profound. That's the ultimate mind blow. The universe is not a collection of facts. It's a story of transformation, of possibility, of constant change. And we're part of that story. Not just as observers, but as participants. Every time we look up at the sky, every time we ask a question, every time we seek to understand the cosmos, we're participating in the universe's process of knowing itself. We're the way the universe explores its own possibilities. And the story of the Milky Way and Andromeda is our story too. Because we're made of the same atoms that make up stars. We're governed by the same laws of physics that govern galaxies. We're part of the same cosmic dance. And whether the galaxies collide or not, whether they merge or miss each other, the story continues. Because the story is not about a single predetermined outcome. It's about the journey. It's about the exploration of possibilities. It's about the constant transformation of matter and energy and structure across billions of years. And that journey is ongoing. It began with the Big Bang 13.8 billion years ago. It continues today with galaxies colliding, stars being born and dying, planets forming, life evolving. And it will continue for trillions of years into the future, long after the Milky Way and Andromeda have either merged or drifted apart, long after the last stars have burned out. The story is bigger than us. It's bigger than our galaxy. It's bigger than any single event or outcome. But we're part of it. And that's the ultimate truth. We're part of the cosmic story. We're part of the universe's ongoing exploration of its own possibilities. And that story is still being written. So when you look up at Andromeda, when you see that faint smudge of light in the night sky, remember this. You're looking at a galaxy with 1 trillion stars. You're looking at a galaxy that has consumed dozens of others. You're looking at a galaxy whose future is uncertain, just like ours. You're looking at a story that's still being told. And you're part of that story. We all are. That's the mind blow. That's the ultimate takeaway. We're not separate from the universe. We are the universe. We're the way the cosmos knows itself, explores itself, tells its own story. And as long as we exist, as long as we look up and wonder, the story continues. The Milky Way and Andromeda might collide, or they might not. But either way, the universe continues. The story continues, and we're part of it. That's beautiful, that's profound, and that's the truth. And that brings us to the end of our journey. Over the past 2.5 hours, we've explored one of the most fascinating cosmic stories of our time, the uncertain future of the Milky Way and Andromeda. We've looked at the evidence that Andromeda is a galactic cannibal, a galaxy that has devoured more than 30 smaller galaxies over billions of years. We've examined the stellar streams and tidal tails that mark the graves of those destroyed galaxies. We've met the victims being consumed right now, galaxies like M32 and M110, slowly losing their stars. We've explored the physics of galactic interactions, understanding why galaxies collide and how gravity and dark matter shape these cosmic dances. We've examined the measurements that first suggested a collision was inevitable, and we've discovered how the 2025 Sawala study changed everything, revealing that the future is far more uncertain than we thought. We've walked through multiple possible futures: the collision scenario where the galaxies merge into Milky, the near-miss scenario where they interact but don't merge, and the distant encounter where they barely affect each other at all. We've considered what all of this means for life, for science, and for our understanding of the universe. And we've confronted the profound philosophical implications of living in a universe where even galactic collisions are uncertain, where the future is not predetermined, where multiple possibilities coexist until one is realized. So what's the key takeaway? It's this: the universe is more complex, more uncertain, and more fascinating than we ever imagined. Our most confident predictions can turn out to be wrong. The future is not written. It's a landscape of probabilities, a branching tree of possibilities. And we're part of that. We're living in uncertainty. Just like the galaxies, we don't know what the future holds, but we can observe, we can measure, we can ask questions, and we can explore the possibilities. That's what science is. It's not about having all the answers. It's about asking the questions, exploring the possibilities, and being honest about what we know and what we don't know. And that's empowering, because it means we're not passive observers. We're participants in the cosmic story. So here's my call to action for you. First, go outside on a clear night and find Andromeda. It's in the constellation Andromeda, visible from the northern hemisphere in the fall and winter, and from parts of the southern hemisphere depending on the season. Look for a faint, fuzzy patch of light. That's Andromeda, a galaxy of 1 trillion stars, 2.5 million light years away. And when you see it, remember, you're looking at an uncertain future. You're looking at a galaxy that might collide with ours or might not. You're looking at a cosmic coin flip that won't be resolved for billions of years. Second, share this knowledge. Tell your friends and family about Andromeda, about the 2025 discovery, about the uncertainty of the future, because knowledge is precious and it's worth sharing. Third, if you enjoyed this deep dive, please consider subscribing to the channel and hitting that bell icon. I create long-form documentaries like this every week, exploring the biggest mysteries in science and space. Your support helps me continue making these videos. And please leave a comment below. Tell me what you thought. What surprised you? What questions do you have? What other topics would you like me to explore? I read every comment, and your feedback shapes the content I create. If you found this video helpful or thought-provoking, share it with someone who might enjoy it. Help spread the knowledge. And finally, keep looking up. Keep asking questions. Keep exploring the cosmos, because the universe is vast and full of wonders, and the more we learn, the more we realize how much we don't know. The story of the Milky Way and Andromeda is just one story among countless others in the cosmos. But it's our story, and it's worth knowing. Thank you for joining me on this journey. Thank you for spending the last 2.5 hours exploring the uncertain future of our galaxy. I hope you found it as fascinating as I did. Remember, we're part of something infinitely larger than ourselves. We're part of the universe. We're part of the story, and the story is still being written. Until next time, keep looking up, keep wondering, and keep exploring the cosmos. Good night.